Okay, so let's go over some examples of countable infinity. So first of all, z plus, the set of positive integers, is countable by definition because it is the thing that we use to do the counting. So z plus is countable by default, as it were. I'm going to say by definition. So what other types of sets are countable? So one, we're going to start with the simplest possible situation I can think of, and that would be the natural numbers. The natural numbers, n is countably infinite. Well, how do we know that? All we want to do to prove that is create a sort of one-to-one correspondence between the positive integers and the natural numbers. So I'm going to line them up here. Positive integers start with 1, 2, 3, 4, 5, dot, dot, dot. And the natural numbers go like this, 0, 1, 2, 3, 4, dot, dot, dot. So how can we make a map? How can we create a function which is going to be a bijection between these two sets? It's very simple. We'll define f from the set of positive integers to the natural numbers by saying f of n, where n could be any positive integer, is going to be what? I bet you can figure it out. The natural number that lines up with the positive integer when we're counting the natural numbers is just one less than the positive integer we're using to count with, right? So this is just going to be n minus 1. Okay, you subtract 1 from the integer and you get a natural number, right? So this is just essentially a shift. We're taking all the positive integers and we're shifting them backwards by one step to produce the natural numbers. And that action of shifting, you can prove that that is a bijection. Okay, so I'm not actually going to prove that because I want to leave that to you as an exercise. So proof that f is a bijection left as an exercise. So try that on your own. I think you'll find it's pretty straightforward. I am going to show you how to do it with a little bit of a more interesting example. The next example I want to go over, 2, the set of integers itself, all the integers, that is also countably infinite. Now what that means is that it's going to have the same cardinality as the natural numbers, because if we can form a one-to-one correspondence between the positive integers and the natural numbers, and if we can also form a one-to-one correspondence between the positive integers and the set of all integers, then it means that they're the same cardinality. So going back here, just remember the definition. Cardinalities are equal if and only if there exists a bijection between them. So if I'm saying that the set of all integers is countable, then what I'm saying is that the set of all integers and the set of just positive integers, those sets are exactly the same size. Now that seems counterintuitive because, hold up a second, isn't the set of positive integers a proper subset of the set of integers? If something is a proper subset, doesn't that mean that it should be smaller in some sense? No, that's what's weird about infinite sets. You can have one set be a proper subset of another one, and yet it's not smaller. They could be exactly the same size. We already saw that here actually with the natural numbers. I just didn't point it out. Right? In fact, actually, the positive integers are a subset, a proper subset of the natural numbers because they don't include 0. It's like adding that one extra element doesn't add 1 to the size of the set because it's infinity. In other words, it's kind of like saying infinity plus 1 is still infinity. If you're talking about cardinal infinity, like the idea of the size of things, at least in a countable sense. May be true in other senses as well, but we haven't got to that yet. So all right, so how are we going to end up proving this? In order to do this, we have to find a way to sort of map the positive integers to all the integers, and to do that, it helps to kind of line them up, kind of like I did with the integers and the naturals over here. So let's start by trying to do that. All right, so my positive integers start at 1, 2, 3, 4, 5. I'm going to go out to 7 here, 6, 7. Now I need to write down the integers. Now, the order that we traditionally write the integers in is from smallest to largest, and that would be starting with negatives and then doing 0 and then going to positives. But there's no starting place, right? Like the integers go off forever towards negative numbers on one side and positive numbers on the other side. So that traditional ordering is not a convenient way to write them down in a systematic way. right? If you're going to write down the integers in a systematic way, you have to have some other approach. So what I'm going to show you is an approach to writing down the integers that starts from 0, and then it kind of works its way outwards in a systematic way. So we're going to go like this, 0, and then 1, -1. And then we'll go 2, -2, and then 3, -3, like that. So let's try to form a map that does this, right? We want to do a map that maps these positive integers to these integers. And if we go on forever, right, if we go on forever, then we will cover this is going to be 1 to 1, first of all, and we're going to cover every single possible integer. We're just going to be covering them half as fast as we're working through the positive integers. Okay, that's all. So this will go on forever. And to form this map, I think it is useful to notice that when we see the positive integers cropping up as outputs, that the inputs are just double that value, right? So when our input is an even number, the output is exactly half that value. When our input is an odd number, that's not the case. Instead, there seems to be a different rule going on. So what we can see here is that what we really need to do is split up this definition, split up this function into two different rules. In fact, it's just going to be a piecewise defined function. So we're going to define our map f from the positive integers to the set of all integers by saying this: f of n will equal one of two different things. If n is even, right, then I've pointed out that the output can be obtained by just dividing it by 2. So it's going to be n divided by 2. All right. However, if n is odd, then I need a different rule. So I'm going to approach this very sort of intuitively. What's really going on here? This idea of dividing by 2 is kind of useful. Maybe we can do that again. If you take 3 and divide it by 2, that's not going to work. But if you take 3 and subtract 1 and get 2 and then divide it by 2, you're going to get 1. That's almost right because this is -1, right? So that's pretty close. If you take 5, reduce it by 1, and then divide by 2, you get 2, right? So again, pretty close. If you take 7, reduce it by 1 to get 6, divide by 2, you get 3. So the approach I'm seeing here, the pattern I'm seeing is well, if I instead of dividing by 2, if I first reduce it by 1 and then divide by 2, and then take the negative of that, that seems to be giving me the right outputs. Let's just double check it with 1 and 0. If you take 1 and reduce it by 1 to 0, and then divide that by 2, well, 0 divided by 2 is still just 0, so that's going to work as well. So there we go. That seems to be working, and we're going to be able to prove that it works in a second here. So I'm going to write negative, and then parentheses, n minus 1 divided by 2. That's the rule that I just came up with. So that's what happens if it's odd. So here we go. We have this piecewise defined function here, and we are going to prove that this is both injective and surjective. So, so my claim that I want to prove here is that f is a bijection. Okay, proving a bijection has two parts. You've got to prove that it's surjective and injective. I'm actually going to start with, I'm going to start with injective. Okay, I want to prove that it is 1 to 1. All right, so to do that, what I'm going to do is suppose that two outputs are equal, and then try to argue that the inputs, the corresponding inputs, would be equal. So I'm going to start by saying, suppose that f of n equals f of m. For some any two n and m in the set of what? Our input, in the set of positive integers. Okay. So suppose f of n equals f of m. Well, what does that mean? I want to use my function, but what am I setting equal to what? Because, f of n could be either of these, depending on whether n is odd or even, and f of m could be either of these as well. So really, we've got several different cases. So case 1, breaking into cases now. Case 1 is the possibility that they're both, n and m are both even. And then in that case, I'm going to get n over 2 equals m over 2. Okay, so that's my first case. Well, if n over 2 equals m over 2, well, then it's pretty clear. I can multiply both sides of that equation by 2 and get n equals m. Great. All right, so that case is perfect. That case is fine, right? Because if f of n equals f of m, all I want to show is that n equals m. So in that case, I'm done. All right, now let's do case 2. Case 2. What if they're both odd? If n and m are both odd, then I can have negative n minus 1 over 2, and that's going to equal negative m minus 1 over 2. In this situation, it is also pretty obvious that, with a little bit of algebra, you can undo all these things, make them both positive, multiply by 2, add 1 to both sides. By algebra, it's pretty easy to show here that m is also going to equal m. Right, so, check, check. Those two cases are good. So I really just have to worry about the third case. I'm going to shift myself up here a little bit and move my third case onto the next page. So case 3 is going to be, what if one of them is even and one of them is odd? Okay, one of n or m is even, the other is odd. Technically, this itself might be two cases, n even and m odd, or vice versa. But since there's symmetry in this statement, f of n equals f of m, I can just say, without loss of generality, let n be even and m be odd. Okay, so I can use Wolog here if I want, and just say one of them is even, the other one's odd, and then I have this. If n is even, then f of n is going to be n over 2, and if m is odd, f of m is going to be negative m minus 1 over 2, like that. So now what? Now what happens? Well, first of all, let's go ahead and multiply both sides by 2. So I'm going to have, scroll myself up here. Let's focus on this. Let's see what happens. Well, I'm going to multiply both sides by 2, and I'm going to get n equals negative m minus 1. Okay, so we have n equals negative m plus 1. And then we're going to have n plus m equals 1. This is a bit troubling. Okay, and the reason is n and m are both positive integers. So n plus m is at least, the least value, the smallest value you could get from n plus m is 1 plus 1, which is 2. Contradiction. So what we found here is we deduced n plus m equals 1, but then since n and m are positive integers, it's actually impossible for this to happen. You can't add two positive integers and get 1, because the smallest possible value you could get is 2, right? And 1 is less than 2. So here's what we've got, backing up. We had three cases. In the first case, we were able to show that, n must equal m. In the second case, we showed n must equal m. And in the third case, we just got a contradiction, so the third case is impossible. Right? So what we've shown is that therefore if n equals f of n equals f of m, let's wrap this up. So if f of n equals f of m, then n equals m in all possible cases. And therefore f is injective. All right, so that's half of our proof. We've proven that it's an injective one-to-one function. Now let's try to prove surjective. Okay, so going back, I'm just going to bring the function back here up above here. All right, here's the function, remember? I want to prove that this is surjective. Now, to prove it's surjective, what I need to do is show that all elements in the codomain, which is the set of all integers, I need to prove that that is that I can always map to anything in the set of integers, right? Well, let's see. What I want to do is I want to consider sort of an arbitrary element of this set, of an arbitrary integer, and then I want to see if I can find a preimage. I want to see if I can find some positive integer that's guaranteed to map there. Now, what we're noticing is that when you have a positive integer as an output, there's a certain way the mapping is defined, right? It's the first row here. And when you have a negative integer or 0, there's a different way that we define the mapping, which is with the second row, right? So I'm probably going to break this into two cases and consider the two possibilities of a positive integer or a non-positive integer. Okay, so I'm going to begin my proof of surjectivity by saying let's let m be an element of the set of integers? Okay, so m is just an arbitrary integer. I've got two possible cases. Either m is positive or m is less than or equal to 0, right? Those are my two cases. So let's look at them one at a time. Case 1, suppose that m is a positive integer. Okay, well then in that situation, that's when I'm dealing with the rule where you just divide by 2. So I bet I can find a number based on this m. I could find a positive integer which is going to map to m. All I've got to do is sort of undo the function. Instead of dividing by 2, I just need to multiply by 2. So then I can say, well, 2m is a set of integers as well. 2m is an integer because m is an integer. Since m is positive, doubling it is still going to be positive. So in particular, 2m is a positive integer. This makes 2m a valid input for my function. So now f of 2m equals, since 2m is even, I should put a note of that, 2m is even, right? It's definitely even because it's multiplied, it's an integer times 2, definitely even. So since 2m is even, when you put it in the function, you're going to use the rule for even inputs, which is take that number and divide it by 2. And that is going to equal m. So thus, m is in the range. Since m was an arbitrary integer, okay, in this case, n is an arbitrary integer. Anything that's a positive integer here is going to be in the range. So that covers case 1. We're good there. So now let's move on to case 2. This is a long proof. So now let's take a look at case 2. So case 2 is suppose that our m we're working with, our integer, is actually less than or equal to 0. Okay, so now I've got to look at the other possible situation. I've got to look at like these, these ones. I'm in one of these cases here. So that's where I'm working with this rule, like that, negative n minus 1 over 2. And so what I can do here is sort of, if I take that negative n minus 1 over 2 and kind of reverse engineer it, I can come up with this. I can come up with, consider, here we go. I'm going to consider 2 times negative m plus 1. Okay, now that is going to be an integer. Since m is already less than or equal to 0, if I make it negative, first of all, if it's 0, then this is 0, and then I have 0 plus 1, which is going to be positive, right? If it's negative, when I take negative m, this will become positive again. And so when I take a positive number times 2 plus 1, it'll still be positive. So this is guaranteed to be a positive integer. So that's also going to be like a valid possible input. Since it is 2 times an integer plus 1, it's also guaranteed to be odd. 2 times negative m plus 1 is odd. So what I've done is I've got this thing, and this is very carefully chosen. I didn't show you my sort of under the hood process of figuring this out, but this is carefully chosen so that it's going to cancel out the function that we're about to apply to it. But it is also a valid input, and it's an odd number. So that means when I do f of 2 times negative m plus 1, I'm going to apply the rule for odd numbers, which was, the rule for odd numbers is negative input minus 1, and then all divided by 2. So I apply that, negative input minus 1, all divided by 2, and then I carefully chose this so that everything nicely cancels out, right? Plus 1 minus 1 is going to cancel. Now I have negative 2 times negative m over 2. Now the 2's cancel, and I have negative negative m, and now the negatives cancel, and this just equals m. And so then I can say, therefore, m is in the range. Okay, I've just proven now that given any, wrong one. Okay, given any integer z, in any integer m in z, right? Any integer m, it's either going to be positive or not positive. If it's positive, then I showed that it's got to be in the range because I was able to like find a pre-image for it, like something that would in the domain that maps to it. And now I've shown if it's not positive, less than or equal to 0, then again it's got to be in the range because I was still able to find a pre-image for it, a valid input that maps to it. So therefore, range equals codomain. So F is surjective. And that completes the proof that it was injective and also surjective, and therefore a bijection. So we can just wrap this up with, therefore, F is a bijection. So since F was mapping the positive integers to the set of all integers, that means that the positive integers and the integers have the same cardinality. So the integers are, so this Z set is countably infinite. All right. Whoa, that's a long one. But I wanted you to see at least one example of this like really formal proof of like, let's prove that let's define a map. Let's prove the map is injective. Let's prove the map is surjective. That shows it's a bijection, that shows these things are the same size or same cardinality, and therefore, that proves this countable infinite nature of the integers. So yeah, this is the main example I chose to show you. Try it again. Like I said, you can. I was leaving this one as an exercise, so try it again if you want with this one. This one is much easier because it doesn't have the piecewise, two cases to work with all the time. But you can take the same approach, proving that the function is both injective and surjective, which establishes a bijection. So there we go.